Welcome to week 2, and we'll be talking about hardware and software. I know the contents are very mathematical, but let me try to explain some of the terms in a simpler manner. Okay, so computer revolution, Moore's law. This is where people have mentioned that the rate of our processing power increases exponentially over time just because we were bound to discover more efficiency in creating our processors, the chips, and making it possible to execute more cycles and in turns that execute more instructions, right? Okay, and before there were a lot of genius ideas that we didn't think was possible, but because of again the improvement in the processing power and then with the memory becoming more and more cheap, right? We are able to build a lot of cool things, right? So having cell phones, right? Before we have a only desktops, and now you do have desktops and phones as well. Having the internet, which is the World Wide Web, and the search engines, right? So classes of computers, personal computers are general purpose, and these are things that you have uh, in your home. You can use it for gaming and for some office and work related, right? Performance requirement varies. Again, if you're a high-end gamer, AAA games, you do need like a lot of high graphic cards. Um, you do need a lot of processing power if you're into audio editing and video editing, the likes of that, right? If you're a heavy programmer with a lot of virtualization as well, when that you're experimenting, you do need higher memory, maybe higher storage space as well. Server computers, on the other hand, are network-based, high capacity, performance, reliability. Uh, are the things that we are basically serving users, and not just one user. It could be a lot, right? Entire organization, entire customer base, or even the public, right? All the consumers. So it can range from small servers. Again, even your personal computer can be a server if you configure it, right? You just open up your port in your computer and then voila, uh, people can access it if you want. And it would range to a building size like a warehouse, right? Supercomputers, these are computers that are very big and they use it for uh, very compute intensive operations, right? Think of it like your quantum computing nowadays, right? Embedded computers are the things that you basically have, let's say, a certain computer or system that does a certain functionality only, right? Or it could be part of a subset, right? An example of this, let's say in your car, you do have a lot of like embedded computers or systems. Let's say an embedded system to just check your engine, right? To just check your oil, right? Those are like some mini computers that basically checks and monitors, right? Post PC era, um, tablet. It was one of the fads, but again, it's not really that of a good use case. I mean, it did become popular, right? But not so much. And this again, this is like around 2012, right? Smartphone sales went up, and it's still steadily going up because it became more and more powerful. And also desktop PCs. Before, a lot of people do buy desktop on their home, but nowadays they just buy laptop as well, right? Personal mobile device, you already have this. Don't need to talk about it. Like it's just things that you usually use or wear. Cloud computing is a very interesting topic where instead of housing your own server, spending a lot of resource, hiring IT people, right? You you can just basically get someone that provides that service, right? So, for example, you have Amazon Web Services, Microsoft Azure, Google Cloud Platform, more of those like Heroku, uh, and many more, right? So you do rent their services, right? I mean, like you do avail their services. So you kind of are renting their servers instead of you buying your own, and that makes it very economical for their business, right? You only pay for what you demand, right? Let's say I need a total of 10 servers for this amount of traffic in my website. They'll give you that, and let's say, okay, I no longer need that because it's no longer Amazon Prime Day. Then let's reduce it to maybe just one server, right? In the normal setup where you house your own servers, it's very painful because you would buy 10 servers and then after the Amazon Prime Day or Black Friday, you end up having a lot of extra servers that you're not really using and you're wasting basically resources there, right? And again, for again because this for managers, this is essentially helpful because before when you buy IT equipment for servers, it's basically a capital expense, right? It's an investment in your part. But if you're using cloud computing, you're basically treating your those servers as your operating expenses now, right? Programming language or translated machine. A good example with this one is um, you have your programming languages. It's somewhat readable to us depending on the programming language, and it just translates to ones and zeros, right? And again, the software has an interface. Another good example for an interface to machine language. Let's say you go to an ATM machine, you do see English language, you see keypads, you enter numbers there that what you want, and in that system, that whatever you entered there would translate that human language or human inputs into basically a query language and into machine language, right? And the machine can now process that and becomes the query language and becomes the user interface and says confirm, right? Or deny. Okay. For performance, you do need to know algorithm. Um, Algorithm is basically a way to check the number of operations executed, irrespective of the processing power, right? Programming language, compiler architecture, it also determines if your programming language is low level, meaning closer to the machine, definitely it's more uh, performant, right? If you do have a high level programming language, farther away for the computer, it tends to be slower. Processor and memory system, higher the better, right? Input output system, okay. 8 great ideas, Moore's law, here we go. The exponential increase through time, through innovation, right? But I believe it's somewhat maybe going to a curve, right, to a ceiling. Abstraction is to simplify the design. Good example is the coffee maker. You as a user, you don't really need to know the intricacies of what's happening inside of the coffee machine. You just press start and it makes the coffee and you get coffee. Right? That is abstraction. The more abstraction you have, the more you don't know inside the system. But the less complicated it is for the user. Again, if let's say there's coffee machine and it lets me do all of the other things inside of it and maybe change how it works, right? It now becomes very complicated to the user. Okay, make the common case fast. Uh, this is something that basically you have to make a design trade-off, right? So favor the frequent case over the infrequent case, meaning if you see something that is a problem which is more frequent, try to solve that first instead of solving that comes in once in a blue moon. Okay, again, this is something that mm, could be fine because we do need to introduce products to the market fast, break things fast, right? Instead of like waiting for a long time, let's say a year, then you introduce that product and it's no longer viable, right? However, there are some products that you do have to wait and check everything. For example, a space shuttle or a spaceship, right? You do want to get all the risk assessment done for that one. Performance via parallelism, you do many things at the same time, right? Pipelining is you put, let's say, things in stages. Let's say you have product or data. Let's say your raw materials and your process, stage 1, stage 2, stage 3, and then you have the output, right? Prediction, example would be data analytics, right? Just going back to pipelining, an example with this one would be data warehousing with your data analytics, aggregation of data, very helpful for financial services, right? Predictions are very helpful for gaining market insights, business intelligence, um, making investments, and then uh, again, decision making. Hierarchies of memories, an example would this be, let's say you have your L1, L2, L3 cache, and that's basically just accessing the faster cache before accessing the slower cache. When I say the cache, it's basically something that they remember you doing, so they store it in a location nearest to the machine. Okay. Dependability versus redundancy via redundancy is basically if you're offering, let's say, a server as a platform where, let's say, you're a cloud service provider, you do want to have multiple servers. So, in the sense that if one goes down, everything just redirects to the other, kind of like load balancing as well. Because if everything goes down and you don't have redundancy, your service is going to go down, and then customer, you would lose a lot of customer and lose a lot of money. Okay, we talk a lot in that slide. We'll make it a bit faster. So you do have application software written in high-level language. These are software that usually you readily use, right? System software is compiler, and you have operating system that manages input output, and the hardware where you open up your laptop, tablet, or CPU, and you see all these components, right? High-level language I mentioned already. Um, a low-level language is basically assembly language, and as you can see on the right-hand side, it just translated from assembly code to ones and zeros, right? So this is encoding and decoding. Components of the computer, desktop, server, embedded. We mentioned that input, output includes user interface, what the user can interact with, right? The display I can see, keyboard I can type, mouse I can move it around. Storage devices. Before we had the spinning platter, hard disk drive. We have the solid state drive now. It doesn't have that spinning platter. We have network adapters for communicating. Touchscreen. We have the resistive and capacity types. Research on that more. And this is how it's being done. Moving along, and as you can see, if you do remove some of the stuff, you would have the same element somehow that you have a board, you do have memory. Moving along, so like you would have the input output, the USB port, the Wi-Fi board, the interface, the video card, the processing CPU cores, right? And again, the best way to really know about this is if you have a CPU or there's something you can open, just open it up and look at it because it does have labels there. And you can basically Google them. Abstraction deals with complexity, mentioned already. Abstraction set architecture, application binary interface. You can move along with this one. That's the place for data. Mentioned about the platter. And now the memories are become smaller and smaller in size, but higher and higher in capacity. In networks, we do have the local area network, which we use the Ethernet. Usually it's colored blue where you plug everything, right? And now you have the wireless network, which is Wi-Fi, Bluetooth. So for the technology trends, electronics communication technology continues to evolve. Again, cost basically goes and goes down, and performance goes up and up. Semiconductor advances to the semiconductor technology. It has now better conduction, better insulation, more switches, right? And this is what they call it a wafer, and this is the processing stage for that one, right? And here's an example of a Intel Core i7 wafer. It's very, very small, right? And 32 nm, you see there, it's nanometers. It's super small. And again, inside of the wafers, it's just basically a lot of like off and off switch to basically process instructions of basically the electric currents. Here's the cost for integrated circuit, right? You can just read about those. Check these graphs as well for performance. And there's a different way to define performance. Again, always think of the trade-offs. Response time, throughput. These are self-explanatory. Let's move along. Relative performance. Elapsed time, CPU time, and again, whatever your operating system, you can check your activity monitor or your system performance to check it in real time. So, clock period, 1 clock, 1 tick, 1 second, 1 cycle is 1 hertz. And if you have a billion of those, 100 billion, I think, would be like gigahertz. So performance improved, reducing number of clock cycles, increasing clock rate. Some computational examples you can go through. Okay. Again, if you do have questions on these computations, feel free to message me in MS Teams. Structured programs, clock cycles, power trends, right? Capacity build times voltage squared times frequency. More computation, and again, remember the CPU. You would try your best to have a cooling mechanism as well. Remember, when you're doing data intensive applications, your fan just shoots up and becomes very loud because it's the way where you're cooling the circuit of the CPU so that it doesn't burn. Right? Meaning burn, not really burn your computer, but it will basically destroy the chip. Right? And we do have some limitations, but if you can't remove more heat or reduce voltage. Oh, interesting stuff as well that for heat, some people have built like a CPU wherein it's basically enclosed in like it looks like an aquarium, right? And you make it work, right? And do a quick Google search here. Water CPU. What is that? Okay, it's called liquid cooling. Do check that out first. And as for performance, look at the increase. And now it's basically constrained by power. Again, power, the output that we're getting in our household has some limitations as well, right? Multiprocessor. If you have more cores, right, more processors, you can basically do more things at the same time. It helps with doing multiple instructions. And for us, most of the time, actually, we think that it's doing things at the same time, but not really. It's just doing things fast or switching things fast in the jobs, right, or process. Okay, check this out. Check this table out too for graph and the computations. And this is the wattage, right? The performance over power. As you can see, as the load goes up, right? The as the power goes up steadily, it's not like a big increase, but as you can see, the performance grows exponentially. About Amdahl's law. Power at idle. The MIPS instruction count. Again, don't be afraid of MIPS. We just do some introductions, but we're not really going to MIPS until you basically do a graduate level with us with computer architecture, which you will be really dealing with MIPS in the few tips and pattern. Okay, so that's for week 2. We've skipped a lot, but that is for your consumption to have a shorter lecture and again, topics that you want to learn more about, I'm always here. Give me a ping. Thank you.